Today we'll be looking at rational functions. Our objectives will be to identify rational functions, to determine the domain of a rational function, to identify vertical asymptotes, and to identify horizontal asymptotes. So let's begin with identifying rational functions. The definition of a rational function is it is a function p of x divided by q of x, where p and q are both polynomials, and q of x cannot be equal to 0. And that just goes back to that fact that a fraction cannot have a denominator that is equal to 0 or it's undefined. The numerator is a polynomial and the denominator is a polynomial. Let me give you some examples of rational functions. I have 2x minus 3 divided by x minus 4. Both of those are polynomials. What if I have 1 divided by the square root of x? Well, let me remind you, the 1 would be okay. That's 1 times x to the 0 power. But the square root of x is not a polynomial. So the second one here is not a rational function. Let's look at the third one. Here we have a polynomial in the numerator, x to the third plus 2x squared minus 5, divided by x squared minus 5x plus 4, which is also a polynomial. So the first one and the third one in this list are both rational functions. Let's now look at the domain of a rational function. The domain of a rational function includes all real numbers except the zeros of the denominator. So let's start with this one. If I give you the rational function 3x minus 4 divided by x plus 7, its domain, remember, are all the x's that are legal for this function. Well, what is the only x that when I plug it in here I get in trouble? It's whatever makes the denominator equal to 0. In this case, the problem area would be x is equal to negative 7. So my domain is equal to all real numbers except x cannot be equal to a negative 7. And let me just make sure that you're understanding. The minute I plug in a negative 7 right here and I add these two, I get a 0 in the denominator of that fraction, and that's why I cannot do that. Let's look at our next example. I have f of x is equal to x plus 6 divided by x squared minus 5x plus 4. Well, you should remember that in order to find the zeros, it would be helpful here if we factored the denominator. So it factors into x minus 4 and x minus 1. Remember, you could FOIL this back together to check it to see that you do get this. But you do, and so what we have here is x minus 4 times x minus 1. The two zeros then are whatever makes this piece over here 0, which would be a 4, and whatever makes this piece 0, which would be a 1. So the two zeros are 4 and 1, so the domain is all real numbers except x cannot be equal to 4 and x cannot be equal to 1. And then let's look at our last one. We have f of x is equal to 2 divided by 2x minus 5. Once again, it is a rational function, and we're asking ourselves for the domain. This time, we still need to know what number we can plug right in here that would make this denominator be 0, but it may not be as easy for you to see that this time. Let me remind you, your step for finding that is to set it equal to 0 and solve. Once you have that, then you can tell me the domain is equal to all real numbers except x cannot be equal to 5/2. Now let's look at finding vertical asymptotes. Let f be a rational function written in lowest terms. First of all, I've given you a rational function. The first question I have for you is it written in lowest terms? That means, can you factor it and remove any common factors? Well, the numerator is okay like it is, but the denominator can be factored. Remember, it's the difference of two squares, so it's x minus 1 and x plus 1. What you want to do then is you want to remember that you have the right to cancel here, and that'll leave you with 1 divided by x plus 1. Once you've reduced this rational function, you're ready to look for vertical asymptotes. The vertical asymptotes will be the zeros of the denominator. Well, in this case, it's whatever would make this right here be 0, so it's x is equal to a negative 1. Now let me show you graphically what that asymptote does. Here's the graph of your original function right here. So that's the graph that I have on the screen right now in blue. Let me show you what an asymptote is. It is a line, and in this case a vertical line. that this graph approaches but never touches, and approaches but never touches. So the asymptote is kind of like a limit line. It's a boundary line that says to the function, you can't cross this line. So you can see once again how you can find that asymptote and then see what it does visually. Now let's look at finding horizontal asymptotes. They're a little more complicated, and there are 3 basic rules you'll need to remember. I do want to point out to you, though, that all 3 rules deal with the degree of the polynomials in the numerator and the denominator of the rational function. So let's look at the first rule. It says if the degree of the numerator is less than the degree of the denominator, then the x-axis is a horizontal asymptote. Now let me remind you, horizontal asymptotes work exactly the same way as vertical asymptotes. It's just at this time the line that we approach but do not cross will be a horizontal line. So its equation will be y is equal to some number instead of x is equal to some number. So let's take an example. If I give you the function f of x is equal to 3 divided by x squared plus 4x plus 4. First of all, this is a rational function, and we want to note, and we now want to see if it has a horizontal asymptote. Rule number 1 says if the degree of the numerator is less than the degree of the denominator. Well, let's look at the degrees of each piece. Let's look at the polynomial in the numerator. It is a constant 3. Its degree is equal to 0. You may not remember this, but it would be the same as having 3 times x to the 0 power. That would just be a 1, remember? So its degree is 0. And the degree of the denominator is 2. Remember, it's the largest exponent you see there, so it's a 2. And so the question is the degree of the numerator less than the degree of the denominator? And if the answer to that question is yes, then the x-axis is a horizontal asymptote. Well, 0 is less than 2, so it is true that the x-axis is a horizontal asymptote. What that means is that I'm expecting there to be an imaginary line at y is equal to 0, which is the x-axis, that the graph will approach as x gets infinitely big and as x gets infinitely small. There's going to be that imaginary border there that the graph will not cross. So let's look at the graph and see if the x-axis is indeed a horizontal asymptote. Well, here's your graph, and I want you to notice that as x gets infinitely large, as it goes out this direction, that blue graph comes down, never does cross, but gets very close to the line y is equal to 0, which is the x-axis. Also notice that as x gets infinitely small, as x's gets smaller and smaller and smaller, the graph does the same thing. So it is true that the x-axis is a horizontal asymptote. I've drawn it in there so that you can see the red line that graph approaches. Let's look at our next rule. If the degree of the numerator equals the degree of the denominator, then y is equal to a divided by b is a horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Let me give you another problem. This time I have a function f of x is equal to 2x squared plus 5 divided by x squared minus 9. The rule says if the degree of the numerator equals the degree of the denominator. So let's first identify those degrees. Well, the first one right here is a 2. The degree of the denominator is also 2. So they're equal. So we're in this situation right here. So we are using rule number 2. To identify what the horizontal asymptote is, I need a and b, where a is the leading coefficient of the numerator. That's that right there. And b is the leading coefficient of the denominator. Well, you don't see it written, but it's an understood 1. So a over b is 2 over 1. So your horizontal asymptote is the line y is equal to 2. Let's look at the graph now and see if we can tell that. Funny looking little graph this time, but that's what it does look like. I'm looking for horizontal asymptotes. So I'm looking for a line that runs horizontally, located at y is equal to 2. The red line I'm about to draw is the horizontal asymptote. Note that as x values get infinitely large, the graph approaches the red line but doesn't touch it. Over here also, same thing happens. As x's get infinitely small, notice that same thing. It's like the red line. The horizontal asymptote is an imaginary boundary that keeps that function above it.
Now I want you to notice it's okay that there's a part of it down here, because what we're looking at is the part of the graph that approaches infinity. So as x's get infinitely big, well, I'm not caring about this part down here at all. I'm only interested in this piece as x gets really big and this piece as x gets really small. So I do indeed have one horizontal asymptote. Before I leave this one, I want to make sure that you do understand. I also do have two vertical asymptotes. I'm just not asking for them this time, is the reason I'm not focusing on them. But if we were looking for that, we would take this denominator, we would factor it into x plus 3 and x minus 3, and then we would look for those asymptotes. And notice that there would be one right here and one right here. The only reason I didn't talk about them before is because that's not what I'm asking you for this time. I'm asking for horizontal asymptotes. So please make sure that you know which one you've been asked for if you're calculating. Now, let's look at our third rule. It says if the degree of the numerator is greater than the degree of the denominator, then there are no horizontal asymptotes. This is by far the easiest of the three rules. If the numerator has the highest degree, then you just quit and go home. There are no horizontal asymptotes, and you go from there. So this is the rule that every time you are identifying horizontal asymptotes, you're hoping that that degree of the numerator will be greater, and you can just say there are none and be done. So those are our three rules for horizontal asymptotes, each of them dealing with the degrees of the numerator and the denominator. That's all I have for you today on rational functions. Have a great rest of the day, and I'll see you again soon. Bye-bye.